In section 4.4, we're looking at centres of mass, and the best advice I have for you here is the same as section 4.3. There are two techniques that we have for all of these questions. One is take the moments, and the other is resolve the forces. So upwards forces equals downwards forces. If there are forces acting left and right, then they must balance out as well, but there rarely are. And clockwise moments equals anti-clockwise moments. And it doesn't matter which point you choose to take moments about, you can usually choose for yourself. But in a lot of questions, there will be an obvious point which intuitively feels like the point to take moments around. Though that's all that we can do. Now, what's changed in these questions is that we have non-uniform rods. Now, the way that that works is it doesn't matter that the rod is not uniform. There is still going to be a centre of mass. So that means if I have a good example of this is a violin bow or a cello bow, which is this sort of shape with some hairs along here, and then at the end where you hold it, there is a big sort of lumpy bit. Now the centre of mass of a violin bow, if you're going to prop up a violin bow with one finger, you need to put your finger about here, and it would balance, about this point here, because this is where all the mass is. Another example would be a hammer, right? You've got a hammer, there we go, there's my terrible drawing of a hammer. You've got a big weight on this end and a relatively small weight with a wooden handle, right? Or with a plastic handle, doesn't matter. If you were going to put your balance the hammer on one finger, where would you have to put your finger? Well, it would be right up here, right next to the hammer head, right? Because that's where all the mass is. But there is still a centre of mass. So if we have a non-uniform rod, we don't have to worry about the centre of mass, we just have to put it not in the centre. So if we're told the rod is non-uniform, then we're going to have the mass not in the centre. So really there are two ways of approaching this. One is that they will give us a question where they say it's not uniform but the centre of mass is here, and they tell us it's a certain distance away from the end. And the other way they do it is that they say it's non-uniform and the mass is such and such. And in example 9 they do the first one of those, in example 10 they do the second one. So in example 10 they tell us the mass is 20, and then we just have to put the centre of mass on somewhere and label it X meters away from the end, and then we work out the X. But it doesn't matter which one of those eventualities we have. What matters is we've only got two techniques to try, so let's try each of those techniques in turn and then look at the equations we've got and solve them, and we'll be away. All right, so example 9, Sam and Tamsin are sitting on a non-uniform plank AB. So here is A to B, starts here at A, goes up here to B, and the whole distance, he tells us, is 4 meters. The plank is pivoted at M, which is the midpoint. So here is M, which is going to be 2 meters away from B and 2 meters away from A. The centre of mass AB is at C, so it's not a uniform plank. The centre of mass is at C, 1.8 meters away from A, but we just put the centre of mass force there. AC is 1.8 meters. Sam has a mass of 35, and Sam is sitting... Tamsin sits at A. Here we are. So there's Tamsin sitting at A with her mass of 25 G newtons acting downwards. Sam has a mass of 35, and we don't know where he's sitting exactly, do we? Let's see. Where must Sam sit for the plank to be horizontal? So we don't know where Sam is sitting. So he's 35 G newtons. But you can see that Sam must be sitting over here somewhere, because if Sam was sitting on this side, then everything would be turning this way. So Sam must be sitting here. Now at the moment, everything's pushing downwards. There must be a reaction force from the support here. I don't know exactly where Sam is sitting. I'm probably going to take moments about the middle though, so I'll label the distance X away from the middle. And there we go. And I've forgotten to put the mass of the plank on there, 25 G newtons. Okay. So I'm going to go for taking moments about the midpoint. But first, because now you'll see that in the textbook they don't do the resolving forces, and that's because in this particular example, resolving forces isn't going to help us, taking moments is going to help us. But we wouldn't know that necessarily in an exam. So I would suggest that when you get one of these questions, you go for both things straight away, and then look at what you can do with the equations that you've got. So I'm going to resolve vertically. Now possibly when you've done a few dozen of these questions, you'll start seeing that actually resolving isn't going to help us here. Moments would have helped us. But I'm going to go for it this way for now. So vertically, upwards I've got R, and that must be equal to 25G, 25G, and 35G. So that is 85G acting downwards. So that's equation number 1, and that tells us the reaction. They haven't asked us for the reaction, but we've got it now, okay. Take moments. You could take moments about A or take moments about B, and actually if you did take moments about A, can you see that there would be a moment from this force here involved, and therefore we would have needed equation 1. But if we take moments about M, which is the more intuitive thing to do, that's the point where the seesaw is going to be tipping, then what do we have? We have clockwise moments and we have anti-clockwise moments. Well, rather than worry about which is which, let's look at each force in turn. That bit's staying still. If I push down, then this would turn this way. That is a clockwise moment. So that is x times 35g on the clockwise side. The anti-clockwise side, if I fix that bit there and I push down here, then it would turn this way. That would be an anti-clockwise moment. So 25g times, now remember this distance here is 2, so that must be 0.2 meters, that distance there, because the whole thing is 4 and this is the center. And then there's also this 25g at a distance of 2. And did you notice I didn't bother checking which direction it's moving there, because it must be turning in the same direction as this one. Just, you know, intuitively these two forces are both pushing down on this side, so it's going this way. Okay, so that is equal to this lot, and now we've really done, haven't we? There's an equation. I know everything in this equation apart from the x, so we've solved the question. So 35x times g, just because we can finish this off, let's do so, equals 0.2 times 25, so that's going to be 5g plus 50g. The g's will all cancel out if you divide everything through by g, so x equals 55 over 35 and that is this distance here. We need to go back to the question, and it says where must Sam sit for the plank to be horizontal, so 55 over 35, so whatever that is as a decimal, that many meters away from M. You'll notice that's a different answer to the one in the book, because the one in the book measures that distance away from A. So they've measured the distance from A to there. Now, if the question was phrased that way in an exam, that would be perfectly reasonable, because this is where must he sit. So I couldn't just give this answer. I would have to say this distance away from M in the direction of B. Okay? And that would be, and obviously give your answer as a decimal, because that fits more sensibly with dealing with meters. In example 10, we have a uniform rod, but we don't know where the centre of mass is. So we have a support called C, a support called D. We're calling the ends A and B. We have a 1 meter distance there, 1.5 meters here, and 0.5 meters there. There is a 3R reaction here and an R reaction here, because it says the reaction at C is 3 times the reaction at D. So this one's called R, this one's called 3R. Now, we have to put on there the weight of the rod acting downwards. Now, can you see that the rod can't have its centre of mass here? Now, why is that? Well, imagine taking moments about C. The question tells us that this thing is still. If we took moments about this C here, this would create a moment anti-clockwise, and this force here would also create an anti-clockwise moment. So this thing would have to be turning anti-clockwise. So it can't be there. And for the same reason, we can't have the centre of mass here, because this thing would then turn clockwise. So we must have the centre of mass somewhere in the middle. And the distance they're asking us for is this distance here, x. Now I'm going to take moments about point C, so I'm going to find this distance y. It's a 20 Newton force, by the way. I'm going to find this distance y from C, and then I'm going to work from there. So that's the setup that I've got. If I've got that sort of setup, I can resolve vertically, and I get 4R equals 20 newtons, so R equals 5 newtons. And I'm going to call that equation number 1. I'm going to take moments. I'm going to take moments about C, because to me that's a more intuitive place to take my moments. And I'm going to get that Y times 20 newtons gives me a clockwise moment, and 1.5 times R gives me an anti-clockwise moment. I'm going to label this one as the clockwise moments equals the anti-clockwise moments. So that's Y equals 1.5 r over 20. I can substitute in from equation 1 and I get y equals 1.5 times 5 over 20. So y equals, well, 5 over 20 is a quarter, isn't it? So 1.5 divided by 4. And if I type that in the calculator, which is perhaps cheating a little bit, there we go, 3/8, y equals 0.375. And that, remember, is this distance y, but I wanted this distance x. So 1 meter plus y. So x, the required answer, is 1.375. Now, that's the answer I've worked out. We've got to be a little bit careful, though, in terms of significant figures. Everything in the question is given to not 4 significant figures. A standard would be, let's go for 3 significant figures. Strictly speaking, in this question, it looks to me like they've given us 2 significant figures in all the measurements. So perhaps we should be giving this as 1.4 to 2 significant figures. In the book, they've been happy with 3 significant figures. And as a rule, if you go for 3, then you probably won't be in any trouble on the mechanics paper. But we have to pay a little bit of attention to that sort of thing every now and then. Okay, that is the end of section 4.4. Good luck.